What's going on, everyone? Welcome back to Structure Free Learning. In this video, we return to mechanics of materials, and in particular, we're going to look at mechanical properties of materials. And what I'm going to try to do is explain the significance of mechanical properties in engineering design, things like yield strength, tensile strength, and then talk about how a tension test is conducted to measure all these mechanical properties, and then identify characteristics of a typical stress-strain curve. Why do we even need mechanical properties? Now, generally speaking, the reason we need mechanical properties is because we want to be able to design stuff, and engineering design is largely associated with trying to prevent things from failing. Like, for instance, how much weight or force can I apply on a bridge before it collapses? Or how many people can I fit in an elevator before the cable snap? In general, you could look at a lot of stuff around you right now, and the reason that it is the way it is so that it doesn't break when you use it. And that, if it's durable, it lasts a long time, it can survive all the loads that you apply to it, you think it's a good design. Now, we take all of these cases of where something could fail, and we define them mathematically by their stresses, the stresses that occurs in the material. And because there's only two types of stresses, most of the time we can just say that what we want is, in our designs, we would like the applied normal stress to be less than or equal to whatever we allow, and we would like the applied shear stress to be less than whatever we allow. Now, in order to put limits on what we define as safe, or we have to define what is considered failure. And this sigma allow, these allowable stresses that we as engineers choose, are a way for us to define how, if or when something fails. And in order for us to define these components, these allowable stresses, we have to have an understanding of how the material behaves that we choose and how it fails. But for us to figure out when the material fails, we need to do a stinking experiment, all right? And really, that experiment, all you need to know is really take a piece of material and break it apart, right? How many times have you done that already before you've had a sense of whether or not it can hold it? You had to touch it, bend it, like buying a shoe. Is the shoe going to be comfortable? So you bend it and it's all flexible, and you're like, oh yes, very flexible. And so, bam, you buy it. So we as engineers want to do this with actual numbers. We want to actually quantify material failure. So now we want to do these experiments and tests so that we can determine the stress at which something breaks, or the most stress that a material can handle. And the most common experiment to do that is what is called a tension test. And the tension test is exactly what it sounds like. It's like taking a material and just pulling it apart. And there are machines that are built specifically to pull and compress materials so that you can break stuff, to do an actual test, and they cost hundreds of thousands of dollars. And what you're looking at here is a servo hydraulic actuator whose real function here is just to move this head up and down, back and forth, so that you can pull apart or push and crush materials that you're going to put inside these grips. This is a picture of another device, same type, same idea, but this one is electromechanical. It doesn't need fluid pressure to provide the force to pull apart materials, but here you can see like hand tightening grip. And here's a picture with a carbon composite specimen put inside for a tension test, and then you can see the extensometer right here clipped at these 2 points. And what the extensometer does is measures the deformation, program it to divide by the original length between these 2 clips, and it'll give you a measure of the normal strain that's occurring within the specimen. And over here, there's a force transducer, and that force transducer measures the amount of force that the actuator is applying, and then you can calculate the stress by dividing by the area. And this is all, set up in some sort of data acquisition system, so it'll make measurements every second or whatever, every 5 seconds or every half second, however fast the processing can work. And then eventually the specimen will look like this for a carbon composite. This one was a pultruded carbon composite specimen, and really all the individual fibers go ping, 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 and then boom, the whole thing breaks. It's pretty crazy. Fibers shooting everywhere. It's kind of dangerous. You got to put some like plexiglass in front and behind just to make sure that the fibers wouldn't come out and shoot and hit people. Most common material that we want to at least get introduced to and be familiar with is steel. Steel is a very popular material to use in lots of structural applications. And so the stress strain curve of steel, you can watch, there's a bunch of YouTube videos. The stress strain test of steel typically involves taking a steel specimen, it's put into the tension testing machine, grabbed at the ends and pulled apart. And you're going to, again, take data measurements, you're going to calculate the deformation, you're going to calculate the stress, and you're going to be able to plot the stress strain curve. And the stress strain curve for steel looks something like this. So this isn't drawn to scale, but it's exaggerated so that we can like identify different regions, and I can write them down here all in one drawing. When we do a stress strain test for a steel specimen, what we have is this first portion right here, from zero load to some increasing load. We have what is called the linear elastic region, which is a straight line, right? Linear, it's a line. And this is called the linear elastic region, which means that it behaves in this region like a rubber band. You can load it and unload it, and it's supposed to return back to its original shape. Once we get to this point right here, this is what we call the yield point. And I've drawn here what is an upper and lower yield point. I think it's enough in mechanics of materials just to know that when you get, you move out of the linear elastic region, that means you've yielded or you've become nonlinear. And this is called sigma y, the yield stress. And once you've reached this yield point, or sometimes is called the proportional limit, you start to have permanent deformation. It's like bending a piece of plastic and it won't go back to its original shape. There's a point where you bend it just enough, and in this region right here, where the loading stays constant, but the specimen continues to elongate, is called the plastic region. Then it seems like the material gets tougher or harder all of a sudden, outside of this plastic region, and somehow it's able to start taking more load again, and the load increases, thus the stress increases until you reach a peak way over here, some peak value, which we'll put boom right here, the maximum or highest point on this curve. This is the ultimate tensile strength, and people call this region up to the ultimate tensile strength, they call this the strain hardening region. And if you talk to a material scientist, they'll say that it's where you've got way too many dislocations and there's no more room left for dislocations, and so the material is able to take on more load and reach this ultimate tensile strength. Another way to look at it is kind of like all the grains and everything lined up, just right as you were in this plastic region, and then all of a sudden it was all lined up and just holding down as much as it could, and now the load starts increasing here. And then finally up to failure. You get to a point after you reach this, it starts decreasing again, the stress that's going on. And here is where we get fracture, sigma fracture. And this would be called the fracture strength, where the specimen physically breaks. In this region, what happens is you will see a noticeable thinning out of this region right here. You will start seeing it kind of stretch and become really, really thin. So the cross-sectional area will get really, really small. It might look something like getting really thin right here, like a neck. And you will see that this is called the necking region. And the values that are really important, or at least the ones that are used the most often in structural steel design, are the ultimate tensile strength, the yield strength or yield stress, and then the slope of the linear elastic region, which is called the modulus of elasticity or Young's modulus. And it's a simple slope calculation, so it'd be like change in sigma over the change in strain, or rise over run. Now, as part of an allowable stress design approach, when you define the allowable stress, this sigma fail over the safety factor, this sigma fail might be, depending on the application, it could be the ultimate tensile strength, it could be the yield strength of the material. And then the safety factor typically is prescribed by codes. In general, with the first course in mechanics of materials, all the equations that we use are assuming that we have a linear elastic material. So for the most part, everything that we do in our material state, we we are in this linear elastic region. Another very important aspect of this linear elastic region is that here is where the linear relationship between stress and strain was observed by Robert Hooke way back in the day. And this relationship, sigma, or this normal stress, is equal to the modulus of elasticity times the normal strain. And this is 1D, or one-dimensional Hooke's law. And this is really important. This is something you should remember for the rest of your life. You know what I'm saying? It's like that important. And to make me remember, I always think of like Captain Hook. Arr! Right? Like a pirate. Anyway. And just to give you a sense of the modulus of elasticity, this Young's modulus for steel is 29,000 ksi. For something like carbon fiber, a high modulus carbon fiber, this could be somewhere around 33,000 ksi. And then concrete is around, a typical concrete would be around 3,600 ksi. And if you look at it, wow, we're talking steel and carbon fiber being about 10 times stiffer than concrete. Another way to look at the stress strain curve is to look at kind of the area underneath. And if you look at the area is like a measure of energy that it takes to break the specimen. And so some cool or interesting properties, in particular because we're talking about stress and strain here, we call that strain energy. But the amount of strain energy it takes to yield the specimen is this area here, and this area is called the modulus of resilience. And you would just literally calculate this. It's a triangle, so 1/2 base times height. Another property, the area under the entire stress strain diagram, this area is called the modulus of toughness. And it's the amount of strain energy it takes to break or fracture the specimen. And you can approximate this or integrate it, provide a polynomial function. Anyway, whatever way you want to calculate the area, you can break it up into rectangles or trapezoidal shapes and add them all up. It's up to you. It's probably easier to do this numerically if you had to be very precise. Alright, so that was a hopefully brief introduction to the stress strain diagram and mechanical properties and why we need mechanical properties in our engineering mechanics and engineering design. Alright, well, let me know if you have any questions below. Structure free.